Okay, guys, let's go ahead and go over the warm-up question. Again, this is in My Open Math. You should have already made your way there and answered this, but there are two questions up here. The first one says, which has more inertia, and then which has more momentum? And you are comparing the inertia and momentum of the two objects up here, a boy riding his bicycle versus a parked truck. The unit that we started last week on Friday with a gizmo had you looking at momentum. But inertia is something that we looked at in our forces unit when we talked about Newton's laws of motion. So you should be able to answer the first question regardless of if you remember what we did on Friday or if you weren't even here. The first question's not really related to that. It's about inertia. Okay, and again, remember, Newton's first law was the law of inertia, and that's the one that stated that an object at rest will stay at rest, and an object in motion will remain in motion with a constant velocity unless an external force acts on it. And inertia was the tendency of the object to resist changes in its state of motion, or its tendency to resist acceleration. Okay, and so if you think about which one of these, a boy on a bicycle or a parked truck, which one would have a greater resistance to acceleration? Which one would be harder for you to accelerate? The truck. Okay, the parked truck would have more inertia. And remember from our previous unit, inertia is directly related to mass. So that first question is basically just, hey, which one has more mass? Okay, because that's the one that's going to have a greater resistance to change in motion. And so the answer to the first question, which has more inertia, is the parked truck. But the second question is what you started looking at in the gizmo that you did on Friday, or at least hopefully did on Friday, and that is which has more momentum. And while momentum is related to mass, it's not the same as inertia. It's not just directly, it's mass determines your momentum. No. Momentum is mass in motion. And we're going to go through some notes today over it because you've just barely started to look at it on your own whenever you did that digital lab. But which one would have more momentum? The boy riding his bicycle or the parked truck? The boy. Okay, the boy riding his bicycle would have more momentum because he's in motion. Okay, the parked truck doesn't have any momentum because it is at rest. Okay, we're going to get into this with our notes today, but please make sure that you have answered the warm-up questions in My Open Math. And then there is going to be an assignment today, 502.1 Momentum Intro Problem Set. That will also be in My Open Math. And today's notes should help get you ready to answer the questions in that assignment. If you don't finish it in class, that will be homework. As I said, we're going to be taking some notes today, so if you don't already have out a notebook, please go ahead and get that out so that you can follow along. And again, you are welcome to open up the slides on your own screen if you'd like to follow along on your own device. But we're going to go through these notes on momentum and talk about what that is, because although you saw it in that digital lab, we have not yet discussed it. Okay, and I don't know what y'all remember after the long weekend, so hopefully some of this is going to sound familiar from what you looked at on Friday, but if not, then again, jot it down. If you were not here on Friday, then you do have an assignment to make up, so please make sure that you complete it, and that is the digital lab that I keep talking about. It's Momentum and Fan Carts gizmo. But let's go ahead and get into the notes. So this is related to the warm-up question I just asked you, inertia and momentum. Again, inertia is resistance to acceleration. It depends on mass. And again, that's Newton's first law of motion that's listed up there. An object at rest will stay at rest. An object in motion will remain in motion at a constant velocity unless acted on by an unbalanced force. Okay, so that is something we've talked about previously. And although they are somewhat related to one another, they are not the same thing, because momentum, okay, is the definition I have up here is the stoppability of an object. Okay, its definition, if you look it up, is referred to normally as mass in motion, but I think it's easier to visualize or understand what that means if you think about how easy or difficult that object would be to stop. Okay, like if I asked if you would rather step in front of a child running 5 meters per second or a bus moving 5 meters per second, pretty sure you're going to pick the child. Okay, I don't think anybody wants to put themselves in front of a bus because, again, it would be harder to stop. That's what I mean by stoppability. So it is mass and motion, but it's related to both mass and velocity. And you're going to see that in the equation in a minute. Okay, so again, not all objects are equally difficult to stop. The measure of the stoppability of an object is called momentum, which is sometimes also referred to as mass in motion. Okay, so inertia is basically just mass. Momentum is mass in motion. Okay, this is the definition, and again, you can write down either, it was on the previous screen, mass in motion or stoppability. The symbol that we use for momentum is not an M because we already use the M for mass. The variable that you will see in the equations for momentum is a lowercase p. Okay, so momentum is p and it comes from Latin. It's patere, to go forward. Okay, so there is a reason it's a p. The unit for momentum is kilogram meters per second. And you're going to see why if you look at the equation. Momentum, p, equals m times v. Momentum equals mass times velocity. Look at these units right here. Kilograms, that's your mass unit. Meters per second, that's your velocity unit. So when you multiply your mass and your velocity, you will get these units. Kilogram meters per second. In order for you to get that, though, of course, when you're using this equation, your masses must be in kilograms and your velocities must be in meters per second. We need those units for other calculations we're going to do later on. So if you do not have kilograms already for your mass, you need to convert it. If we give you a velocity in some units other than meters per second, you need to convert it. Okay, unless that particular question, tells you otherwise. Okay, so again, you will want to use those units because we're going to do some calculations after today in which you're going to need things to be able to cancel. Of course, you also want these units today as well. So momentum, again, the variable or symbol is a p. The equation p equals m times v. That m is mass. Okay, so please don't get that mixed up. Students do that sometimes since momentum does start with an m. So make sure that you're aware that that's mass and that the p is momentum. Okay, looking at that equation, you can see then that if you have zero velocity, like the parked truck in our warm-up question, that you will also have zero momentum. Okay, just look at the equation. If you plug in a 0 for velocity, you will get a momentum of 0. Okay, that is why even though the truck had more mass, because it was at rest, it had 0 momentum. Okay, so if you're not moving, you don't have momentum. Momentum is a vector quantity, which again means that it has both magnitude and direction. So whenever you are reporting an answer for momentum, you're going to have a direction with it, forward or to the left or a positive or a negative number, okay, as well as the actual quantity, the magnitude of the value, which means your momentum can be negative, okay, because negative is a way that we denote direction in physics. Being in the negative direction, you will have a negative momentum. So if you have an object moving forward with a velocity of 5 meters per second, it's going to have some amount of positive momentum because it's going forward. If, on the other hand, that same object were moving backwards with a velocity of -5, then again, mathematically, you would get a negative number for your momentum. Okay, so your momentum will be in the same direction as your velocity. Of course, mass doesn't have direction, but your velocity does. So your momentum will be in the same direction as your velocity. All right, so let's see if we can answer a couple of little questions here. The first one says the speed of a particle is doubled. By what factor is its momentum changed? Okay, again, that equation is momentum equals mass times velocity. So it's saying, hey, if you were to double that velocity, that speed, okay, if you were to double that, what does that do to your momentum? What do y'all think? What is that relationship going to look like? Doubles it. Yeah, it's going to be a directly proportional relationship between velocity and momentum. You can see that in the equation as well if you have that written down in your notes. Okay, what about the second question? Do you think it's possible for a bullet to have the same momentum as a truck? I'll give you a moment to think about that one. You can turn and talk to your neighbor You have 26 seconds to discuss, but I'm going to call on somebody, so make sure you have an answer ready for that second question. Can a bullet have the same momentum as a truck? All right. What do we think, Anna? Yes, it can. It depends on the velocity. Yeah, the easiest way for them to have the same momentum, by the way, is if they're both at rest. Okay, they can obviously both have 0. Okay, but if you had a bullet with a very small mass, because bullets are pretty small, moving really fast, and a truck, which has quite a bit of mass by comparison, moving really, really slow, it is possible for them to have the same amount of momentum, or of course they could both be at rest. Okay, but yes, it is possible. It depends on not just the mass. These do have very different masses, but also their velocities. Okay, so again, we just looked at that. Doubling that velocity does cause this to double as well. That's that directly proportional relationship I was talking about. And again, yes, both can be 0 if both are stationary, or if the bullet is traveling fast enough and the truck is moving slow enough, they could be equal to each other. All right, let's do an example calculation. We just had the equation a second ago on the screen, so we're going to use it. It says a 55 kilogram man is riding his bike with a constant velocity of 7 meters per second. What is the momentum of the man? I think you're going to find these calculations pretty straightforward because it is just a 3-variable equation. But we're still going to go through the process of labeling everything, because as we know from our previous units, usually the first day the math looks pretty easy and then we start adding more and more stuff. So we need to make sure we can keep it all straight. So let's go ahead and label it. The mass that we're going to be working with here is 55 kilograms. The velocity is 7 meters per second. We're looking for, our unknown is momentum, which is a P. Okay, the equation, of course, is the one we just looked at. Momentum equals mass times velocity. And so that's all you're going to do is plug in. Really easy. 55 times 7, that's it. Okay, 55 times 7, if you type that into your calculator, is going to give you an answer of 385. And again, your units will be kilograms times meters per second, because this was 55 kilograms times 7 meters per second. So that's where that unit came from, but that is your momentum unit. Okay, so again, this math should be pretty easy because it's just 3 variables today. We're going to obviously be adding more, but for now, today's assignment, I don't think you're going to find the math too tricky. All right, let's try this one. A baseball has a momentum of 45 kilogram meters per second. If the ball has a mass of 0.5 kilograms, how fast is it traveling? I'm going to give you guys a moment to see if you can answer this. I think you probably can. I don't think you all found that last one too difficult. Okay, so see if you can set this up. At the very least, label everything and get the equation written down. But see if you can come up with the answer for how fast is it traveling. I'll give y'all 25 seconds. If you would like a calculator, you can grab one from the side. Okay, so let's work through it. Hopefully you had enough time to at least get started on it. Maybe you got the answer. It should be pretty quick. But let's label our givens. We have a momentum of 45 kilogram meters per second, and we have a mass of 0.5 kilograms. Luckily, my units already matched. I don't have to do anything with them. Okay, I can leave it as is and just plug into my equation to solve for the velocity. The equation, of course, being P equals m times v. That is, momentum equals mass times velocity. When you substitute in, it looks like this. 45 equals 0.5 times v. If you want to isolate that variable and get this v by itself, you need to divide both sides by 0.5. 45 divided by 0.5 gives me a velocity of 90 meters per second. Okay, so the velocity of this baseball is 90 meters per second, which is really fast. So I don't know how that, it definitely wasn't thrown by a person. That's okay though. But that is it. Did you guys get this one? Thumbs up? We're good with that? Yeah? Okay. Let's try looking at a graph. It says Jack and Jill ran up a hill at a constant velocity. Jack's motion is shown by line A and Jill's is shown by line B. If both have the same mass, who has a greater momentum? Going all the way back to Unit 1 with this. But this is a position time graph. And position time graphs I can use to find velocity. And if they both have the same mass, I'm really just looking at, hey, who has a greater velocity? Because that person is going to have a greater momentum. So which one has a greater velocity, A or B? I heard somebody say it a second ago. Which one's faster, A or B? Okay, how do we know A is faster? Steeper slope. That's all we're looking for here. Okay, now if I wanted to calculate it, then I would need to get the value of the slope and I would need to know the mass. Okay, and I could ask you to do that, so just be prepared. But yeah, the steeper line here is going to represent the faster velocity. Therefore, line A, which is Jack would have a greater momentum. Okay. All right, here, let's put some numbers to it. Says, again, same scenario. If both Jack and Jill have a mass of 75 kilograms, find the momentum for each of them. Okay, you guys just told me that the slope represents the velocity. The steeper slope is faster, but you can also get a number value for that slope. Okay, for line A, again, slope is rise over run. A is easy because it goes through the origin. Okay, so you go from 0, 0 to pick any point, but I'm going to pick the last one. Okay, and rise over run from here to there is 20 over 10, which gives me a slope of 2 meters per second. Okay, so for line A, which is Jack, his mass is 75, his velocity is 2. If I want to get his momentum, it's just 75 times 2, which is 150 kilogram meters per second. For line B, again, still the same mass, 75, but we need to get the slope. This one's trickier. You can't just pick the last point and say, oh, 15 over 20. That's not going to work because it doesn't go through the origin. And yet I still see some of y'all doing that sometimes. Again, pick any 2 points on the line. It doesn't matter which two as long as they're on the line. So we can pick the starting point and the end point. That's fine. It just doesn't start at 0, 0. It goes from 5 to 15. That's rise of 10. Run of 10. 10 over 10, of course, is 1. And so for Jill, 75 times 1, her momentum is 75 kilogram meters per second. So again, we can use stuff all the way back from the very beginning of the year, Unit 1, and use a graph like this one to determine the momentum of Jack and Jill or whatever the object may be. Questions about the graphs? Okay. All right, so again, momentum is a quantity of motion of an object found by the equation P equals m times v. Objects moving with constant motion will experience constant momentum. Okay, but how can you change the momentum of an object? Yeah, if you change the velocity. How could we cause the velocity of an object to change? I know it's early, okay? But we can change its velocity, we can make it accelerate, okay? And how do we make things accelerate?
Add
Force. Okay, yeah, if you apply a force, okay, you can cause the velocity of an object to change, push it, pull it, something, or maybe friction just does it for you, okay? But you can cause the momentum of an object to change if you apply a force to that object. See, everything's coming full circle. We're bringing everything in from the whole year. We just talked about Unit 1, and now we're talking about the last unit we just did, and we talked about inertia, so we're bringing everything together. That's how this class is. Each unit, we're just adding one more thing, okay? And just like we had a bunch of equations on our board before, I'm sure you can imagine there will be a bunch more because we're going to be adding to that. Okay, but yeah, you can apply a force, and that's going to cause your object to accelerate, which of course would cause its momentum to change because you changed its velocity. Okay, again, momentum is measure of stoppability of an object. How do we stop it? You just told me that. A net force. Okay, a net force is required to accelerate or stop an object. If we apply a net force, we cause the velocity and thus the momentum to change. Again, F net equals m times a. That's where we're getting that from. If we apply a net force to our object, we will get acceleration, which means our velocity changes, which means our momentum will change as well. Okay, the application of force for a certain time is called impulse. Okay, that's a definition that you might want to write down. The application of force for a certain time is called impulse. And we're going to talk more about impulse a little bit today, but we'll get more into it tomorrow as well. The whole unit, really. This is momentum and impulse, technically. All right, so let's go ahead and get our definition for impulse, and I had one up there a second ago, but it is change in momentum due to a force that is applied for a certain period of time. Okay, now the variable that we use for impulse is not an I, and I don't really have a reason for this one. It may be from Latin, I don't know. I know that the P is, but we use I later on in the year for current, which again doesn't make sense because that doesn't start with an I. But we're using J for impulse, okay, J. So the variable that you'll see in the equation is a J. The units for impulse are Newton seconds, Newtons times seconds. And if you look at the equation, again, it's going to make sense because the equation says J, which again is impulse, equals force times time. It's in the definition too, change in momentum due to a force applied for a certain period of time, force times time. Okay, so you're going to have an impulse, you're going to have a change in momentum if you apply a force for a certain amount of time, and the units for force are newtons and the units for time are seconds. So when you multiply newtons times seconds, of course you're going to get this unit, Newton seconds. Your forces therefore must be in newtons, your time therefore must be in seconds. Okay, so impulse, change in momentum due to a force that is applied for a certain period of time. So again, let's do an example calculation for this one. It says, a 55 kilogram man is riding his bike with a velocity of 7 meters per second. That sounds familiar because we did this in our last one, except now he applies 20 newtons of force from his brakes for 19.25 seconds to come to a stop. What is the impulse acting on the bike? Now he's changing his velocity, and that means you're going to have a change in momentum due to an impulse. Okay, so we're going to, again, label the information that we have been given. We know that the man has a mass of 55 kilograms. We know that the man has an initial velocity of 7 meters per second, that he applies 20 newtons of force from his brakes. Okay, that means he's applying the force in the opposite direction that he's moving. So that's going to be negative 20 whenever I write it down. You have to pay really close attention to things like that so you get the right sign. But that force is going to be opposite whatever direction he's moving. So since I called his velocity positive 7, his force applied from his brakes is negative 20. Okay, we know that the time that is applied is 19.25 seconds, and we know that he comes to a stop. I didn't actually label that, but I could have labeled his final velocity as 0. Okay, the unknown that we are solving for is impulse, which is J. Okay, so J equals, and then our equation for J is F times T, force times time. So there's a lot of extra information up here that we don't actually need in this particular calculation. Okay, all we need is the force and the time. So substituting in, that is negative 20 times 19.25. When I multiply those together, I get an answer of negative 385 Newton seconds. Which, if you recall from the first question we did, I said, hey, what is this guy's momentum if he's riding his bike at 7 meters per second constant velocity, and your answer was 385 newtons? Well, guess what? He just lost all of his momentum because he stopped. So look at his impulse, negative 385. He lost it all. Okay, if you look back to that question earlier, it was 385, now it's negative 385 since he stopped. Okay, your impulse will give you your change in momentum. It will be the same, it's the same thing as change in momentum. We're going to talk more about that later. Okay, so negative 385 Newton seconds. All right, let's try this one. A 0.06 kilogram pool ball experiences a 33.8 Newton second impulse when it's struck by a pool cue for 0.72 seconds. What is the force acting on the ball? Again, I'm going to give you guys a minute to see if you can figure this out. So why don't you try labeling the information you have and see if you can figure out how to solve for force with the information given to you in this question. You can turn it and talk to your neighbor if you need to. I'm going to give you a minute to or 26 seconds to try to figure it out. Okay, it's okay if you haven't finished it. I just want to see if you can get started on it. If you did finish it, even better. Okay, but let's see what we can label in this particular question. Sorry, let me turn off the timer. The given information, we have a mass of 0.06 kilograms. We have an impulse of 33.8 Newton seconds. We have the time of that collision is 0.72 seconds, and we're looking for an unknown force. Okay, again, the equations that we have two right now, but in order to find force, only one of those equations has force in it. It's this one, J equals F times T. And so we're going to plug in impulse equals force times time. Our impulse being 33.8 equals F times our time being 0.72. Again, you're trying to solve for force, so you need to isolate this variable. These are being multiplied, so if you divide both sides by 0.72, 33.8 divided by 0.72 will give you your force, and that will give you a value of 46.9 newtons. Again, maybe you got that one on your own, hopefully so. As I said, these aren't too tricky. There's only 3 variables up here. We're going to add more stuff later, but for now, both of these equations are pretty straightforward. Does anybody have a question about this one? Okay. All right, so change in momentum. Again, a change in momentum occurs when an object accelerates or changes its velocity due to an impulse. Change in momentum is delta P. Again, delta in math terms means change, okay, and P is momentum. So delta P is change in momentum. The units for change in momentum are kilogram meters per second, and the equation is delta P, or change in momentum equals mass times change in velocity. If your velocity changes, so will your momentum. Okay, and it will change due to an impulse. We've already looked at that. Okay, your masses, of course, must be in kilograms. Your change in velocity must be in meters per second. As a note, change in velocity can be calculated if you're given a final and initial velocity by subtraction. Final velocity minus initial velocity. Because a lot of times the question's not going to say the change in velocity is 5 meters per second. It's going to say the object was moving 2 meters per second and now it's moving 7 meters per second. And you have to say, okay, the change is positive 5. Okay, or whatever the change might be. So if you want to write this down as well, you can, but change in anything is always final minus initial. Change in position, final minus initial. Change in velocity, final minus initial velocity in this case. Okay, so again, change in momentum occurs when an object accelerates due to an impulse. Okay, so you guys saw this in the fan cart gizmo that you were looking at last week. Okay, so you had a scenario like this where your fan cart was moving with an initial velocity and this fan was causing it to come to a stop. Okay, and so looking at this, you could say that the net force acting on that fan cart, I don't know if I have this filled in, yeah, it was to the left. Okay, it was slowing it down. The cart's moving to the right, but the force is to the left. Okay, the acceleration, therefore, also to the left. You can actually see it. Well, I don't know how well y'all can read this, but this says negative 0.27. Y'all saw this again last week. But your velocity is to the right. Okay, it's decreasing to 0, but it starts out, with a velocity of, and I didn't see where it started, but maybe 2. I can't remember. I'll wait till it resets and we'll look at the animation up here. But you have an initial velocity of 2, and then it's decreasing to 0, but it's positive 2 all the way until you get to 0. But you're moving forward, and your momentum, because your velocity decreases to 0, so does your momentum decreases to 0. So y'all were looking at this in that simulation and answering questions about it as well. But you're going to be seeing all of these different terms, which you've seen force before. You've seen acceleration. We had a unit on force. We had a unit on acceleration. We had a unit on velocity, and we're bringing it again all together. All right, this one says, 4 moving crates are experiencing the forces shown. Which diagram or diagrams, there are 4, A, B, C, D, which ones show momentum changing, which ones show momentum not changing? Okay, remember, you're going to have a change in momentum if you have acceleration. Okay, when are you going to have acceleration? Looking at a free body diagram. When it's unbalanced, right? So all you're looking for here, which diagrams show momentum changing, you're looking for unbalanced forces. Unbalanced forces mean you're going to accelerate, that means your momentum is going to change. On the other hand, momentum won't change if your free body diagram shows balanced forces, because that means that object is moving at a constant velocity or not moving at all. Regardless of if it's constant or at rest, your momentum will not be changing. Okay, so where is our momentum changing? Well, let's see. Diagram A, definitely unbalanced, so this would have changing momentum. What about B? Is this going to have changing momentum? Is that balanced? No, so yes, this will have a changing momentum. So A and B both. What about C? Nope, that one's balanced. Okay, that will not have a change in momentum, but D will. Okay, so A, B, and D all show scenarios where your momentum would be changing. The only diagram that shows a scenario where your momentum would not be changing, or where you have constant momentum, would be diagram C. Okay, so again, you can go back to free body diagrams like these and answer questions relating to momentum based on whether or not you're going to have a acceleration or not. Okay, one of the most common real-world tie-ins with this unit is going to be with regards to car crashes. And we're going to talk about some car safety features and stuff like that too. But I have a video here. I'm not going to show it to you because it's 26 minutes long. But it is a really good video. So if you happen to have some time and you want to watch it, it's got a lot of good information in it. But it says, watch this video for real-world applications of concepts of momentum, impulse, and Newton's laws of motion. Again, I'm recommending it, but it is optional. I don't have time to show it in class. So I put it in the slides so you can go back and look at it. But it's got a lot of good information, and I would recommend that you look at it. For the rest of the class period today, you can either watch that video if you like, or you can make your way to My Open Math and work on the assignment. This is not correct. It's not due tomorrow. I need to change that. The assignment is due by tonight at 11:59 p.m. I need to fix that. That is not correct. 502.1 Momentum Intro Problem Set. So this is what you're working on. If you have any missing work, which at this point is basically just if you didn't do your gizmo, then please make sure you get that taken care of as well. Okay, but again, this is due tonight. Ignore this. It's not tomorrow. I'll fix the slide. If you have questions as you're working, let me know. You guys have about 15 minutes, so you have a lot of time to at least get it opened up, work together, ask for help rather if you have any questions. 1 second, Braden.